Okay, I think we waited enough, so it's my pleasure to Denis talk about characterization of metric spaces with a metric fundamental class.
Yes, yeah, thank you. Sorry for the terrible long title. Well, first of all, thank you for the opportunity to give this talk today. Yes, I will talk about the topic I was working on the last 3 years doing my PhD, and I kind of try to give you a little overview of what we managed to do. And, well, generally speaking, the idea is that we try to represent the fundamental class of a non-smooth manifold using an integral current. And we're going to call this representation be an integral current, the metric fundamental class of this non-smooth manifold. But let me point out that this notion of metric fundamental class is definitely not standard. It's something we came up with in the recent paper with Terry. So if at the end of the talk somebody has an idea for a better name, please let me know. We're still looking for ideas. But let me maybe start with the smooth setting and then try to motivate this problem. So let M be a closed, oriented, and connected Riemannian manifold. So all manifolds in this talk are going to be closed, oriented, and connected. So from now on, we'll just drop this usually, just maybe for the first time. Okay. So in this case, we know that the singular homology of M with respect to the integers, well, this is just top dimensional, it's just the integers, right? Because it's oriented. And we call the generator of this group the fundamental class of M. So now, a priori, this generator is just a purely topological object, right? Because you look at the singular homology, and we would like to have a representation of this generator, which also has some analytic properties or more geometric properties. And the good thing is, since we have a Riemannian manifold, we can actually represent this generator as a Lipschitz chain. So, in particular, we have the following. We have that this is actually the same as the singular Lipschitz homology, where we look at not only singular chains, but Lipschitz chains. So now, for example, we can already talk about the volume of such a chain, which is, well, better to work with. So here I mean a Lipschitz chain C is given by, well, it's just the finite sum of some integer coefficients, and we have Lipschitz simplices. So here the coefficients are again integers, and the maps are from the standard simplex indicates place into M, and they're Lipschitz. And now I would like also to introduce the integral current. So I won't give the proper definition of an integral current because it's quite technical, but I try to give you more like a vague definition, so which I hope give you some intuition later on. So now an integral current, which sometimes you can see it as a generalization or an extension of this concept of a Lipschitz chain. T. This big N, capital N, is going to be the space of all integral currents, dimension n in M. Put the dimension here, sorry. So it's something very similar. This time, first of all, we allow countable sums. Again, we have integer coefficients. And now I change with the notation. Just a bit more standard. So again, we have integer coefficients, and now this k, this ki, they're just compact sets in free space in Rn. Now the big difference is that we allow the compact sets to have empty interior, which of course gives us much more flexibility. And the phi again, they are Lipschitz maps from this compact set. Well now, and we have a finite mass condition for T and also the boundary. What I mean with that is that because now we have a countable sum, we need some kind of finiteness condition so that the volume is finite. And also since we allow any compact set, it's not clear that the boundary is finite at the end, right? Sorry.
Can you just recall the definition for the bracket for the ki?
Sorry, yeah. Well, the thing with the ki is that this is now an anchor in Euclidean space, and well, an anchor takes a differential form. Well, I'm going to work with metric currents later on. So what I'm going to take, I take n plus 1 Lipschitz maps. This is the argument. What's going to happen is I just integrate over the compact set, like this. And then
This ki is
then yeah, well, you have to. Well, usually you allow like add 1 maps per base. Yeah, I just want to make an analogy to that. Yeah, well, the thing important part is now that again we have that actually if the boundary is finite, also the boundary is going to be an integral current. So we can look at the homology via integral currents, and it turns out that this is also isomorphic to all these homology theories. At least for manifolds, they agree in the top dimension, or in every dimension. And in particular, we can represent this homology class as an integral current. The question we were studying, I was studying the last 3 years, is like, what happens for a non-smooth manifold? How does this picture look in this case? So, what I mean with a non-smooth manifold, I mean a metric space. Which is homomorphic to M, and we assume that it has finite Hausdorff n measure. So, first of all, Mx is of course also a manifold, topologically speaking, but it can be well. It's not smooth. It's not smooth, so you can have a lot of singularities. And but we assume that the Hausdorff n measure is finite. This kind of avoids X to be a fractal. For example, the Van Koch snowflake is also topologically just a circle, but of course, Hausdorff one measure in this case wouldn't be finite. And why we need this is because, as you may guess, we notice that there's a strong connection between integral currents and rectifiable sets. And this condition that the Hausdorff n measure is finite guarantees us there are a lot of rectifiable pieces. So we have at least a chance to construct an integral current like this. Yeah, and the question is now, what happens? Well, first of all, topologically nothing changed, so of course the singular homology is just going to be set again. The question is what happens with the Lipschitz homology, singular Lipschitz homology, or with the homology via integral currents. And now the problem is that Lipschitz chains, they are not suitable for this setting, and it may happen, we have examples for that there are no top-dimensional Lipschitz chains. So it may happen that this is just going to be 0. And the problem is really that we look at maps from the simplex, so from an open set or open or non-empty interior, and this is kind of too restrictive. So we are only left with the integral currents. And the question is, can we now say something about what level of that? And for this, now I will come to this definition, because at the end we try to represent this whole fundamental class of X as an integral current. So we also expect this integral current to have some additional properties, which kind of represent. So that's the definition. So an integral current in X is called a metric fundamental class of X. If, well, first of all, if it has no boundary. I recall that we look at closed manifolds. So also the fundamental class should have no boundary. Then we want that there exists a constant such that the mass measure of T, and we'll say something about this in a minute, is bounded from above up to a constant by the Hausdorff measure. So people who are less familiar with currents, you can think of this as the analog or generalization of the volume measure of the manifold, and we want to have some kind of relation to the Hausdorff measure, to the metric. So in the smooth setting, we actually have equality here, but it's way too much to ask for. Also, the lower bound is also kind of even much stronger than the upper bound, so we kind of are happy with this. And secondly, if we look at the push forward on the Lipschitz map into, so we have a Lipschitz map from X or non-smooth manifold and a smooth manifold. We push forward this current, then we expect it to, we want it to be the degree of F times, well, the fundamental class of F. This is exactly what.
This is the first condition. You want the constant to depend just on n, because otherwise we are finite. Okay.
Yeah, that's the problem. We would like that. Before, we're not sure. We tried to prove that if there exists a constant, then at the end it has to depend on n, but we didn't manage. Later on, I will show you some existence, and in this case, it's going to only depend on n. Yeah. Yeah. But since we're not sure, we just stick with that, and so far it's good enough. But yeah, that's a good point. Yeah, yeah, and this, yeah, and then this. You don't see this. This shows you that this current actually has some connection to the topology of the space, which a priori is not clear if you look at the definition, because we allow random, arbitrary compact sets. So maybe let me give you a lemma to kind of convince you that this is actually a good definition. So if T, such a metric fundamental class exists, then we have what we want. We have that the homology of X is actually just that. And this T is the generator. So in order to get this picture, at least the left side, it suffices to show or to construct such a current. That's kind of what we want to do. So, yeah, sure.
But it may happen that in this generality the space In of X consists only of the zero current, or?
Yeah, that's that's the thing. Okay, this kind of tells you, well, either it's just zero or it's set. But I don't know. I don't know. That's kind of the whole project is to. We think that it should always be this under these assumptions, but we cannot. I will give you some existence when it's this case, and I will give some characterization showing that, well, we don't have the full picture now. However, in certain cases we do, and actually, if we go back to the setting of last week, the Marx box, so in 2D, so basically, we want the dimension to be 2, so X is just a metric surface, and M is a remaining surface. In this case, we have the perfect, very good understanding. And we could prove, let's joint work with Giuliano Basso, who was here in Bonn, and my supervisor Stefan Wenger. Hello. For surfaces, we know that there exists always a metric fundamental class. And we have a uniform constant for that for this inequality. So there we get exactly what we want. Yeah, universal constant. Sorry. So there exists a constant which doesn't depend on m such that this holds. Yes.
So how do you define the degree of a map from a metric space into a manifold?
Topological degree?
Yeah. But like, so I usually think of it, I think mostly of manifolds, and I think it's like multiplication of fundamental classes, but I guess we don't have that here.
You can see that it's the multiplication of the fundamental class in terms of the singular homology.
Right.
And we want that this also holds for.
Oh, yes, okay. Yeah.
But this is exactly the number you get if you look at the singular, the topological one.
Right.
We wanted the same equality holds for the analytic metric conversion. Yeah, that's going to be one.
Is there an easy example when the constant is not 1 for surfaces?
Some
surface where you don't get just
this one?
of t is equal to Hausdorff is.
Yeah, you need to look at some Finsler manifold where you take, I call it, but you have these different norms on each tangent space. If you don't take them to be Euclidean, then it's not one, right? That's what's happening.
The surface is compact.
Yes.
Different norms are equivalent, right?
Yeah, they're equivalent. Yes. Yeah, exactly. Yeah, exactly. That's exactly that's going to happen. Yeah.
But the multiplicity is 1 everywhere, yeah?
Yes. Yeah, that's the point because you look at the different volume. I don't know the word. Yeah. Because you look at the way you how is it? That's the norm of the differential forms you call it co-mass norm, and so it's equivalent, but it's not the same as the Hausdorff measure. Yeah, that's why if it's 1, then you have a universal constant, right? So, okay, maybe let me say something about the way you prove this is that you either you can use this uniformization theory Amaris was explaining last week to kind of construct this current, or there's another nice result about metric surfaces which gives you this. And it turns out that if you have a metric surface, we find an area, then you can approximate the surface by polyhedral surface with controlled geometry, controlled area. And using this approximation, one can construct this fundamental class. So this is a theorem by, I'm very sure I pronounced the name wrong, Paramtekos and Romney. So, in that, we look at the two-dimensional case, then there exists a sequence of polyhedral surfaces which are homomorphic to X. Such that the following two properties hold. First of all, each of these homomorphism is a rough isometry. And it also doesn't distort the area too much. So there exists a constant such that we'll make a picture afterwards to explain it a bit better. For all compact things. So, what does this mean? It means that here that we have our metal surface, X, and then we can find a sequence of polyhedral surface, that's not very nice, Xi and homomorphisms. And these homomorphisms, they don't distort the distance too much, and they don't distort the volume too much, the area, sorry, in this case. It's actually one of the main tools to prove this uniformization results. And now, using this, it's not too hard to construct a fundamental class, fundamental class in X. So sketch of the proof. Well, the idea is that each of the polyhedral surface has a metric fundamental class. Then if you look at the total mass, the area of these things, we have, well, this bound for the mass measure for a universal constant. And then by this inequality, we also know that the area of each of these polyhedral surfaces is bounded by the area of the metric surface. So in particular, we have a uniform bound for the mass of this sequence. Then we can use a compactness theorem to pass to a weak limit of this, which, since we have this form of Hausdorff convergence, if you want to do it correctly, one can show that this actually lives in X. And then, well, because each of those is a cycle, we get that the limit is also a cycle. And then using a local version of this argument for the mass bound and lower semi-continuity, one can prove the first inequality, the first property of fundamental class, and then the second one also passes to the limit. And for this we use the fact that these maps, this rough isometry, is actually homomorphisms. So at each, yeah. It's not that hard. I don't want to go into the I hope it's more or less complex. But I just want to show that we use both of these properties are important. And now, of course, this approach would also work in higher dimensions, right? So if we have any manifold, well, non-smooth manifold, we can approximate it with nice manifolds in a controlled way, with controlled volume. Then we can construct a fundamental metric fundamental class also in the non-smooth higher dimensions. However, the problem is that to obtain such a theorem for higher dimensions is quite complicated. Nevertheless, we managed to show that under an additional assumption in higher dimensions, having such an approximation is actually equivalent to have a metric fundamental class. And that's Because the proof of this relies strongly on the two-dimensional geometry, so we cannot just copy-paste it for higher dimensions. This is joint work with Terry. Unfortunately, I had to leave last week. So, just let me repeat like the whole setup. I'm sorry, it's quite of a long statement. So, you have metric space. Which is homomorphic to remaining manifold. Well, again, it's always closed, oriented, and then connected. And we suppose that the Hausdorff n measure is finite to avoid the fractal something. And now we also want that the Nagata dimension is finite. I will say something about this later on. This, for example, holds if x is doubling. So if all these properties hold, then the following are equivalent. First, we know that well, x has a fundamental class, metric fundamental class. And now I'm just going to basically write this down in the slide variation again. So there exist metric spaces. They are now not polyhedral surfaces, but they are bi-Lipschitz equivalent to M, to the smooth manifold. So they are Lipschitz manifolds. And again, they are homeomorphic to M to X. And it's the same thing, just for completeness. This is the constant such that the volume is bounded. So,
And they are polyhedral manifold now.
excuse me?
And now this xi are polyhedral manifold, or what is the assumption of xi?
I didn't hear.
Xi are polyhedral manifold?
No, this time they are not. This time they are bi-Lipschitz to M, so they're Lipschitz manifolds. So in the sense that they're metric spaces and you have Lipschitz charts into a Euclidean space. So, yeah,
So why just a sense, like, why you need this xi and you don't write everything on x itself? Just to understand that if there's no assumption this xi, why you need them?
The xi?
Yes.
Well, because in xi we know that we can represent the fundamental class as a current.
Okay.
And from this we can pass to the limit using these properties to construct the current in the non-smooth.
Okay, thanks. Good.
Yeah, that's yeah. Of course, polyhedral would be a bit nicer, but just get an effect. Yeah, kind of. Yeah. Okay, perfect. Okay. Yeah, the same proof, the same idea works. So if you have such an approximation by nice spaces, you can pass the limit and you get your current. And kind of the more interesting part is that it's actually equivalent. If you have such a representation of the fundamental class as a current, you can construct such an approximation. That's what I'm saying. The way we do this, we show that there's actually a third property which is also equivalent to all these properties, to both of these properties. And then we get for this implies this implies this, and then we do the full circle. And it's again a bit technical, I'm sorry, but so this third property involves bounds for the local degree of Lipschitz maps. That's kind of the idea. So you can exist constant such that if you look at the Lipschitz map from X into Euclidean space, Lipschitz, and we assume it's like bi-Lipschitz on a compact set. And for almost all points on this compact set, and I'll explain this further afterwards. And then for almost all points, we have that the local degree is bounded by this constant t. So, the way you should think about this is the following. So, we have our metric space X. Now, because we have a finite Hausdorff measure, we can decompose it into two parts. The rectifiable part, which is the good part somehow, and the purely unrectifiable part, which is the bad part. And we cannot guarantee any control, we don't want, of the local degree on this unrectifiable part because it's the bad part. But we want only control on the rectifiable part. And this says that if you now have a Lipschitz map into Euclidean space, then there may be a part which gets collapsed, right? Oh, like green is not a good color. This part may get collapsed, so on this part the local degree may not be defined. So only for but for the rest we know that for almost all points, on the part which doesn't get collapsed, we can make sense of the local degree, and there we want to have control of the local degree. So maybe if you're more used to the smooth setting, this is quite trivial actually, because if X is smooth, well, the local degree this is just the sign of the determinant of the differential at this point. This is quite standard, right? And also here you see, I mean, if X is smooth, we don't have a bad part, the whole manifold is rectifiable. And then by Salt theorem or Lipschitz version of that theorem, we know that on the part where we don't get, which doesn't collapse, the determinant, well, it's differentiable for almost all points and it's non-degenerate. For these points, we actually have this equality, and it's just 1. So in the smooth case, it's just going to be 1, it's quite trivial. But in the non-smooth case, it's quite tough to get somehow.
Yeah. Could you give an example of a bi-Lipschitz map that has like degree 2 at a point?
Bi-Lipschitz?
Yeah.
The branch cover of C with a Z to Z squared. At point 0, you get around twice.
Yeah.
But it's not bi-Lipschitz around 0, or is it?
Yes.
The point, right? So the way I see this being bigger than 1 is you wind, but then you're not bi-Lipschitz.
Yeah, the thing is, honest. No, to be honest, we kind of hope, or we still hope that this third property is true anyway. But we have no clue how to prove it, that's kind of the problem. Usually the idea is you show that you have this degree bounds, then using these degree bounds, you construct this approximation by Lipschitz manifolds, and that's how you get your current. But at the moment, we don't know how to get this bounds for the local degree, except we assume already we have a fundamental class. That's where you get like the full circle.
Now the point of the question is how can you have degree 2 if you are bi-Lipschitz? If you zoom in, you're like isometric, right, around a point.
Yeah, almost everywhere.
Yes, almost everywhere. You want the degree bound also only almost everywhere.
No, but if you zoom in, there's a big piece where it's isometric, right?
Yeah.
But this big piece is not an open set. You have a compact set which is, if you zoom in, has density 1, and on this piece it's isometric. For the local degree, to look at local degree, you need to look at open sets. And actually this part, there's a part, so you have a part where you don't have control and this messes the whole thing up. Maybe I can explain you afterwards.
Sorry, the example I said is still true.
Do you have
We take a cone over a large circle, take a homeomorphic so take a cone over this.
No.
No, it's again as before. We expect it to be one, but we don't know how to do it. I mean, I'm maybe not selling my result not very good, but yeah, we don't have an example where this doesn't exist.
I mean,
Yeah. Like I said,
what's the set on which it is?
I think if you
So it's
this is
two topological planes.
To give some
One is the flat plane, the other thing has a large cone angle.
Yeah.
approximation.
So now what?
The approach to solve this you prove what I don't know. Except under this additional concept, condition I show you now, I prove my
By a bijection. And then you take the Euclidean cone over that.
Okay.
The degree is a billion. I don't know the definitions of these things. Yeah, I think I can explain it later.
Yeah. So, okay, let me finish maybe with another existence result. Which then combined with this result gives you kind of some sufficient conditions when you can get this approximation. So maybe first I have to define what it means to be linearly locally contractible. So we say a metric space is linearly locally contractible, or LLC for short, if X is some constant such that each ball is contractible for all x. It's contractible within a bigger ball of the same center, but we now enlarged radius exactly by this factor. I mean, for example, every manifold is locally contractible, and it's linearly locally contractible is a quantitative version of this property. Yeah. What you should think of is that if you have a manifold and we have maybe some spike growing out, look at the surface, and I take a ball here with a radius big enough that it wraps around the spike, this ball is not contractible, and in order to contract the ball, I need to go all the way up, right? So this constant is going to depend on the diameter times the height, basically. And this tells you that you may have spikes, but they cannot get worse and worse and worse on all scales. That's what it tells you. It says. Or otherwise, you cannot have like bottlenecks. Well, you can have bottlenecks, but they cannot get worse. Let's limit how bad they are. And under this assumption, using a different technique, we can also construct such a fundamental class, and in this setting, we get also the perfect constant. So, this was again proven by Giuliano, my supervisor, Stefan. And we get even a stronger result. So we then have it's homeomorphic to a closed Riemannian-oriented manifold. We have the finite Hausdorff n measure, LLC. Then we have a fundamental class. And we have a lower bound for the measure for the balls. And there exists constant such that if you look at the measure of a ball, this is bounded from below by a radius. This gives you some additional. And if you think of these spikes, maybe not that surprising, right? Because I told you that if it's linearly locally contractible, then you can have spikes, but they cannot be very bad. Well, there's some limit how bad they are. And this volume bound fails exactly at the tip of these spikes, right? It's kind of. And this actually implies that you also have the lower bound for the mass. Yeah. And just as a corollary, I mean, so far I only explained to you when these objects exist, but I didn't really explain to you how we use them. So maybe just one small corollary. In this case, X is we can conclude that X is rectifiable. Because you won't have to be a bit careful, because it's possible that there exists like an integral current like this, or metric fundamental class, without X being rectifiable. It has to be a rectifiable subset, but not the whole space has to be rectifiable. But this condition here tells you that in this case it has to be rectified. So, I think this was known in 2D already using different techniques, but using that result we can also generalize it to higher dimensions. And you get also the bound for the Hausdorff measure, right? Which was also not known before. Yeah, but I think maybe I stop here.